How's it going, ladies and gentlemen? Mr. Johnny here again, looking at 12.6 voltaic cells. We want to be able to describe how differences in metal activity are used to make voltaic cells, which make batteries. Batteries are made up of voltaic cells. So this should be something that is important to you because, you got mobile devices, you got anything that runs on a battery has to do with this kind of chemistry. All right. So specifically, we want to be able to label and explain the components of a voltaic cell. We want to be able to look at it and go, this is what this part is what this part is what it does. We want to be able to label the anode and the cathode, explain what happens at each one of those. Label the salt bridge, describe why the salt bridge is important, why do we need one of those. What is the load? Direction of electron flow, which way are they going? And also direction of the anion and the cation flow. So those are all the things we want to be able to do. All right, so metal activities. You got table J, shows you different activities in the metals. Let's say, for example, we had zinc and the zinc ion, and we had copper and the copper ion. Where are they? Here's zinc, and there's copper. So the question is, well, what would happen if I had these things and I mix them together? Well, I know that zinc is more active because it's higher up. So zinc wants to be oxidized. So if I had zinc metal and I put it in a solution that had the copper ion in it, we would get a reaction because zinc is going to be like, hey, I want to be oxidized more than you. So we'd end up with zinc becoming +2 and copper being reduced to copper 0. Now, so what? Why is that helpful? Well, just mixing those two together wouldn't be all that helpful. But if you could somehow separate the zinc and the copper ion, that transfer of electrons from zinc to copper, well, moving electrons is electricity. And you can use that electricity to text your sweetie. Be like, hey, sweetie, OMG, raffle, lamau, LOL, whatever you got to send. Probably something more important than that. So what you do is you put them in different containers, because if you had just one container with the copper ion and the zinc metal, well, the electrons are going to be transferred directly to each other right where the zinc hits the copper, and we don't want that. So what you got to do is you got to put zinc in another beaker that's going to have the zinc ion in it too, right? So we get another big beaker with zinc nitrate or something. So now we also need to do the same for the other one. We got to take a strip of copper and we put it into that copper nitrate solution, right? So now the electrons want to go from zinc to the copper ions, but they got no way of getting there. So what we're going to do is we're going to give them a way to get there. We're going to give them a wire, right? So we're going to connect the two metal strips with wires, and we're going to put our load, the thing that we want to power, in between them. So now the electrons will have to go through the thing we're trying to power in order to get to the copper +2 ions. So the only way for the electrons to get there is going through the device that we want to power. Right? There's one important part missing, and I'll explain why it's really important, is the salt bridge. So we need a salt bridge that also connects those two cells, right? So if this is a voltaic cell, this whole thing is a voltaic cell. Well, then this beaker here is a half cell, and then this beaker here is a half cell. Sometimes, you'll see it referred to as in the oxidation half cell. It's just the one of the beakers where the oxidation is occurring, right? So why is the salt bridge important? We'll get to that. But once you have the salt bridge, then you can actually get some power. You'll power that voltmeter, and you can see how much voltage is being produced. So what is happening here? All right, so we have this setup. We have voltage. We have electrons being transferred. So what's happening is that the zinc is being oxidized, and we call this the anode. So the zinc is the anode, right? And it's being oxidized, which you got to remember is losing electrons. It is the negatively charged electrode in a voltaic cell because it's shooting off electrons. That's where the negative stuff is coming from, right? So we got these electrons being lost by zinc, which is going to become the zinc +2 ion because it's losing those electrons, and it's going to dissolve into the solution. Right, so we got the zinc +2 ion being produced because the zinc's losing those electrons. Well, what do those electrons do? They travel through the wire and through the load and into the copper electrode. So you can see the electrons going through, and then that's why we get this voltage. It's producing power from those electrons passing through it. So now we're getting a buildup of electrons onto this copper electrode. Well, electrons are negative, and I know in solution I got copper plus 2 ions. So what's going to happen? Oh, I totally jumped the gun. Copper is the positive electrode, and it is called the cathode. All right, so we got anode for oxidation, we got cathode for reduction. Anode's negative, cathode's positive. So what's going to happen is those electrons are going to be hanging out onto that metal copper plate, and it's going to attract the copper plus 2 ions, right? They're oppositely charged. Those electrons are going to end up going to the copper plus 2. So the copper is attracted to that copper bar, the electrode, and it's going to absorb those electrons and become copper metal and actually plate onto the copper itself, which is going to make this electrode bigger, right? Because we're taking copper out of solution, we're adding it onto that bar. All right, so the last part that is critical is the nitrate ions. The salt bridge here is really important. It's a bridge for salt to travel across. Because what would happen is, well, I'm going to get a buildup of positive charge in this beaker if zinc keeps losing electrons. I'm going to get a buildup of negative charge in this beaker if electrons keep going over there. And it's going to get to the point where an electron is going to be like, hey, that's way too negative. I'm not going down there. Because, negative charges repel negative charges. So it wouldn't happen. You need a way to get rid of that extra negative charge on the other side. So that's where the salt bridge comes into play. The nitrate ions that are hanging out over here are going to be able to travel across the salt bridge to the other side as such, right? Nitrate's going to go across, which means we're going to get rid of some of this negative charge over here. And that nitrate's going to combine with the zinc plus 2 ions. So we're going to get this as our overall reaction. I know you're probably confused at this point, which is okay. Confusion's good. Well, I mean, it's a good first step. And you're probably overwhelmed. You're probably wishing at this point, I wish there was some catchy way to remember all of this information, because, it's a lot. Well, fortunately for you, there is a music video done by a Mark Rosengarten. Mr. Rosengarten over in Washington made an excellent music video that I encourage you to sing along with. I promise you this, it will get stuck in your head, and you will be glad that it did, because it will cover like 90% of this unit. All right, so here it is.
Vital to make a battery is this electrochemistry. You take 2 half cells and connect them up so well, with a load to power in between. You need to have electrodes, you see, full of that metallicity. Let electrons flow, across the salt bridge we go, allowing us to make electricity. We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where?
Everybody now!
We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? We start at the anode, electrons are lost there, and go through the wire, and through the load on fire. They enter the cathode, and reduce the cations, and the anions go through the salt bridge back to where? We start at the anode, electrons are lost there, and go through the wire. and through the load on fire, they enter the cathode and reduce the cations, and the anions go through the salt bridge back to where?
Where?
We start at the anode, electrons are lost there, and go through the wire, and through the load on fire, they enter the cathode and reduce the cations, and the anions go through the salt bridge back to where?
Where?
We start at the anode, electrons are lost there, and go through the wire, and through the load on fire, they enter the cathode and reduce the cations, and the anions go through the salt bridge back to where?
Where?
We start at the anode, electrons are lost there, and go through the wire, and through the load on fire, they enter the cathode and reduce the cations, and the anions go through the salt bridge back to where?
Where?
The anode!
All right, so I hope you like that. And I hope it's stuck in your head, and I hope that you're singing it in class because I will be playing it. All right, so some tricks. So we got some vocab and stuff that is new. Some tricks to remembering it. Can you remember an ox? You know, I'm literally thinking of like an ox. Like I can't draw for beans, but I'm gonna try. You know, that's the legs, and then yeah, I'm not gonna draw. I can't draw, but an ox. And what that mnemonic is for is helping you to remember where the anode is where oxidation occurs. All right, so anox, you remember anode, oxidation. And then red cat gets fat. Literally picture a red cat getting fat. What that stands for is, where's my pen at? Reduction occurs at the cathode, which gets fatter. It gets, it gets bigger. Because it's reducing those ions into the metal form, and the metals are going to bind to it. It's going to get bigger. All right, so yeah, the cathode is getting bigger because cations are being reduced to their neutral form and attaching to the electrode. All right, the anode does the opposite, and it gets smaller, right, because it's losing stuff and its ions are dissolving. All right, so let's do a little practice. So here's an example set up. I got nickel sulfate and nickel, and I got barium sulfate and barium. So the first thing to ask is, well, which one of these things is going to go through oxidation? So that's where I look at table J, and I'm going to find these metals. Found nickel, and now I'm looking for barium. Barium's up here. Barium is the more active one, so it is going to be the one that gets oxidized. All right, well, what does that mean? Barium is the anode of the cathode. I don't know. All right, wait. Oh, it just had a trick. Anox. So the anode is wherever oxidation occurs. So no, barium is going to be my anode, which means nickel is going to be my cathode. All right. Well, now let's think about this. Oxidation is losing electrons, so I have electrons starting over at the barium, and they're going to go to the cathode. So remember that electrons always flow from anode to cathode, always. Because the anode is where oxidation is occurring. So that's where those electrons are starting. That's where they're first being kicked out, kicked off or kicked out at the anode. So the electrons start at the anode, they go to the cathode. That means the thing in between is always going to be labeled the load, the thing that you're powering. Right? So here it's just a voltmeter. It could be a cell phone, it could be anything that's using that power. All right, well, what's this thing again? This is a salt bridge. All right, so I got electrons going this way. So you start at the anode, electrons are lost there, and go through the wire and through the load on fire. They enter the cathode and reduce the cations. All right, so we got reduction going over here. Well, what's being reduced? It's the nickel plus 2 ions being reduced by gaining 2 electrons, I'm becoming the nickel metal, Ni0. Oh wait, backtrack. Barium, if that's being oxidized, I start off as barium 0, and it's losing 2 electrons. So I got those 2 electrons going through the wire and through the load and fire. They enter the cathode and reduce the cations. And the anions flow through the salt bridge back to where? The anode. So they're going back towards the anode. The cations are doing the opposite, right? And I'm running out of room over here, but the cations are going to flow to the cathode. So that's basically what you need to be able to do. So you start at the anode, which is the more active of the metals, right? So barium's more active. Start there. You start at the anode. Electrons will also go through the wire and through the load and fire. They enter the cathode and reduce the cations, and the anions flow through the salt bridge back to where? The anode. All right, cool. Yeah, we're gonna call it. That's pretty much it. We'll do some practice in class. Rewatch the video. Rewatch the music video, and bring questions. I'll see you then.